Well, good afternoon. It is 12:25. I'm running late. Well, I was running somewhat late, but then when no one was here, I went down to clear my head again. It didn't seem like I did a very good job of it. But I had like 3 or 4 interruptions at lunch, so I just got up here a few minutes late. No one was here, so I went to, like I said. But I'm here now, and I'm the only one in the room. It's supposed to be Calculus 3, and I'll just continue. Let me just go a couple of announcements. Number one, it probably will already be over with by the time this loads, but my office hours normally on Wednesday are 3:15 to 5:15. However, I've got a meeting this afternoon on the Birmingham campus, so I will be tied up there. I'll leave campus as soon as my differential equations class gets over at 3:15 or shortly thereafter. So I'll be on the Birmingham campus. The meeting is supposed to be 4 to 5-ish or so. I've got to leave by 5:15, so it wouldn't make any sense for me to come back here. I'll just stay over there. So anyway, that's that. I think I announced to you before, but just to say it again, Tuesday, Thursday, my office hours are now 1:15 until 3:15. They weren't first mini-term, but they are this mini-term because the Physical Science 2 class is starting 2 hours later, 3:15 to 8 o'clock, or 7:45, rather than 1:15 to 5:45. So I'll be here later in the evening, but I'll have 2 hours office hours in the middle. Okay, and I guess one other thing. I'm behind in getting grades entered on Blackboard. I hope to be able to catch up with those. I can't today because of the meeting, but maybe tomorrow. I've still got to be working on my spring schedule, so there's a lot of things piled up right now, but I'll try to get the grades in tomorrow if possible. Okay, that being said, where we left off before was in Chapter 13, Calculus of Vector Value Functions, Section 13.5, Motions in Free Space, and we're just about the middle of page 724. And that starts with talking about linear motion. Acceleration is the rate at which an object is speeding up or slowing down. That's in linear motion, if you're moving in a straight line. The acceleration is 0 if the speed is constant. But a contrast to this, in 2 or 3 dimensions, the sorry, man, my throat hurts. The acceleration can be non-zero even when the object speed is constant. This happens when the velocity v is magnitude of the velocity vector v, okay, is constant, but the direction of the vector v is changing. The simplest example of that is uniform circular motion, which is what this figure is illustrating. Okay? And that's figure 4 point here. Okay? Now, as you can see, in uniform circular motion, the object obviously is going counterclockwise around the green circle. But at any given moment, its velocity is tangential to that circle. Its acceleration for the uniform circular motion is toward the center of that circle. Okay? Well, you might say if it's uniform circular motion, constant speed, how can it have velocity? Well, let's just take a point just a little bit past that point and draw another tangent vector there. Well, you see the velocity, his magnitude is the same, but the displacement is different. So I'm going to try to do this. It'll be so small it's really hard to tell. Let's just take, let me get my pen activated. Okay. Say this point right here. Okay, now the tangential vector is something like this. Okay, a little bit of a change from there. So if you put this point here at the end of this one, there, the acceleration would be toward the center of the circle. That's a pretty lousy drawing, but that would reflect what's going on in that illustration. The acceleration is always toward the center of the circle. Okay? That's so ugly, I think I'm going to erase it. Oops. Wrong eraser. All right. Blow it up again. Okay. So wherever you are, the velocity is tangential to the circle, but equal length. That's why they call it uniform circular motion. But the acceleration is perpendicular to that toward the center of the circle. Okay? So that's just an example of how some could be going at a constant speed, but still accelerating. If you're traveling in a curve, around the curve. Linear motion, no, it wouldn't happen that way. All right. Here are the three formulas we have. Well, before we get there, let's go back and let's do example 5. What we're looking for here is A of t. That's the acceleration vector as a function of t, and the magnitude of the acceleration vector as a function of t. For motion around a circle of radius r, so let's use this circle down here and say that radius is r, with a constant speed of v. So the v, which is not the vector v, the scalar v, is constant. That means the speed is constant. Okay? Now, oh, goodness gracious. Says, assume the particle follows a circular path, and here would be the circular path to use. R of t, if it's a uniform circular motion, the circular path would be, the magnitude would be r, and circle in trig notation, you might say, the x-coordinate is your cosine theta, and your y-coordinate is sine theta. Okay? Now that's a unit vector, because cosine squared theta plus sine squared theta is 1. So that is a unit vector of magnitude r, length of radius r. And we were told it had that. Well, its first derivative, r prime of t, is the velocity vector as a function of t. And that would be r times derivative of cosine t would be minus sine t. Derivative of sine t is cosine t. Okay? So that's your magnitude of your velocity. That's the actual velocity vector. Well, evidently didn't write down everything. Yeah, I wrote it down there. Okay, got it. All right. Now, let's take the derivative of the velocity vector, which is the second derivative of your displacement vector, which is the first derivative of your velocity vector, and that will be your acceleration vector, which is the first thing that we were asked for there. Okay? What is that? First derivative of that would be r times minus cosine t. Derivative of minus sine t is minus cosine t. Derivative of cosine t is minus sine t. Now, that explains, if you think about this, at any position here, your displacement vector is this vector r, pointing outward, okay, pointing toward the circle. Well, exactly opposite that is your acceleration vector, pointing toward the center of the circle. So that's why this one is exactly opposite that one. Okay? Okay. So there's your acceleration vector that answers that question. Magnitude of that would be remember, this is a unit vector. Cosine squared plus sine squared is equal to 1. So the magnitude of that acceleration vector, for some strange reason, is also r. Now that doesn't seem like it makes sense, but I guess it does. Let's see. Oh, wait. Sorry, I left off something. Okay. Let's back up. Sorry, I got carried away. I was forgetting. I started off in thetas, and I should have been in t's, but I'm going to blow something up here. A lot of this will stay the same, but there is some other stuff we got to do with it. So, all right. I think sorry about this. Okay. Theta is the angle, and let me blow this up a little bit. Okay. If this is your angle theta, that's what I was putting down there. I needed it in terms of t. Well, what is theta? Okay. Well, it comes from this. d theta dt is equal to omega. Okay? Now, that means probably I shouldn't use d's here, because it's not really a derivative. It is true in the long run, but at any time here, the change of theta over change of time is your angular speed. Okay? Theta is an angle. The rate of change of an angle over time is the angular speed, which we call omega. So then we say theta is equal to omega t. That's what I should put in here. It is theta, but it should be written as omega t. Okay, so when you take the first derivative of that, it's minus sine omega t times the derivative with respect to t of omega t, which introduces an omega. Because the same thing happens here. That will be a minus sine omega t cosine omega t, and you have omega in front of it. Pull both of those out, and you got omega t. Then when you take derivative of that with respect to t, this is now is an omega here and omega there. Okay? Derivative, and you had an omega here, and derivative of minus sine omega t is negative cosine omega t times another omega, which gives you an omega square there. And derivative of cosine omega t is negative sine omega t with another omega, which contributes to that same omega squared. So there is your acceleration vector. That's what we were looking for up here. Okay? So, now, the magnitude of this is what's in front, r omega squared, because this squared plus this squared is still equal to 1. You still got a unit vector in there, so your magnitude is what's on the outside, omega squared. So that is your second part. Now, think that's okay. Here's another relationship for you. Your omega is the rate of change of your theta. The rate of change of your velocity, since that's related to your radius, r, and the angle theta, the change of sorry, I'm having trouble breathing. Like I told you, I was racing through lunch, and because of the interruptions I had, so I didn't drink enough fluid while at lunch. I think that's one reason my head's clogging up now. Plus the fact this room is awfully cold. First class, they don't turn on the fans and things like this until 8 o'clock, so the room was comfortable to begin with. Had a room full of students, so it remained being comfortable, and then slowly cooled down, but I didn't notice it before lunch. But now it's quite chilly, so sorry about that. Now, that's all sad story of my existence here. Let's go back to arc length. This arc length here, S, is equal to r theta. Okay? If theta is measured in radians, that's true. Okay? The let's put that capital R because that's what we're using as our radius here. Okay. Now, that's a constant. Your arc length is a variable here, and that depends, the change of the arc length, the change of direction doing, that's your velocity. Okay? The change of theta, that's your omega. Okay? So this tells you, if you take the time derivative of that, r being a constant, then you do ds is equal to r d theta. Well, ds is velocity. It's equal to r times omega, because change of theta is your omega. So there's a relationship, very much parallels to what we just did. Okay? Now, if you'll note from here, you can then also say that since r omega is velocity, this is also speed, okay, times omega, okay, v omega. Now, v being speed here, okay? Or, another way you can express that is get velocity out of the picture. No. Get omega out of the picture. And omega is equal to v over r. Right? So we'll have r times v over r, v squared over r squared. Well, one of the r's cancels out, and you have v squared over r. And that's your classic definition for your magnitude of your acceleration. And we call that the centripetal acceleration, and that's v squared over r. Your speed squared divided by the radius. Okay? That's what the thing underneath example 5 is talking about. All right. Enough of that. Let's go to understanding the acceleration vector. Let's go back through a little bit of review of what we've done before. You start out with a displacement vector, r of t. You take a derivative of that, r prime of t, and that's your velocity vector. Okay. Now, the velocity vector of any curve, not just a circle, but of any curve, is the tangent line to that curve. Okay? So, the unit vector along that tangent line is called the unit tangent vector. Well, the unit tangent vector is in the direction of velocity because the velocity is always tangent to the curve. So your unit tangent vector is equal to the velocity vector, okay, divided by the magnitude of that velocity vector, because it's in the direction of the velocity vector, but with magnitude 1. And if you divide the velocity vector by its magnitude, you're guaranteed to have a unit vector in the direction of that velocity vector. So there's the first little equation we have, and that's at the bottom of page 724. We've had it before, okay? Now, remember what you do once you have a unit tangent vector? You can take the derivative of that unit tangent vector, okay? And that will give you the time rate of change of that unit tangent vector as you're moving along the curve, okay? Now, the unit tangent vector is a unit vector. The derivative of the unit tangent vector is not necessarily a unit vector. It may be or may not be. But the vector, okay, how to say this? The change of the unit tangent vector is always going to point toward the center of the curvature of that portion of the graph there. And that's where the time rate of change, the first derivative of the unit tangent vector will point. That is in the direction of the normal vector. So the normal vector, the unit normal vector, this is a unit vector, is that derivative of the unit tangent vector, which may not be, usually isn't a unit vector. So since it isn't, divided by the magnitude of the derivative of the unit tangent vector. Okay. So that's the second equation at the bottom. All right. Now, oh my goodness gracious. Let's go back to this formula here. Rewrite this as V of t is equal to the magnitude of V of t, which, to keep from writing magnitude any longer, let's just write that. And the book writes it as italicized V. I can't write in italics, but let's just call it V of t. That is the speed, magnitude of the acceleration vector. That's what this is, times the unit tangent vector. Okay? So the velocity vector is in the direction of the unit tangent vector, tangent to the curve at that point, with a magnitude of the speed. Because the unit tangent vector has speed of magnitude of 1. Okay? Now, so here's another expression for the unit, for the velocity vector. Now we already said the acceleration vector is the first derivative of the unit of the velocity vector. Okay? And since the velocity vector is a product, a scalar times a vector, we can use the product rule, and that would be V of t, t prime, can't write, plus v prime of t, oops. So used to writing v as a vector. This is a velocity function. V of t times the unit tangent vector's first derivative of t. All right, that was the product rule. No. I got lost what I was doing there. Okay. This is the first derivative of the speed. Okay. The first derivative of the speed times the unit tangent vector. All right. Yuck. Now they wrote theirs in the reverse order. I think I'm going to have to go down and get something to drink. I'm having a harder and harder time talking. So let me put this on pause. All right. Similar to last time, whatever I did, it didn't seem to help a lot. But here's what we had, and I think I'll write that a little bit neater here. A of t, which is derivative of v of t, dt, but using this definition, and this time I'll write it in the same order the book does. V prime of t times the unit tangent vector plus the speed times the first derivative of the unit tangent vector, which, by the way, I keep reminding you, is not necessarily a unit vector anymore. The unit tangent vector is, its first derivative is not necessarily. Okay. Now, another reminder, okay? If you go back, they tell you in section 3.13.4, okay? And you can look at one of two places. The summary on page 718 is there. It's near the middle bullet in the summary. It's toward the bottom of the summary. But if you want the box that shows it, that is on page 715. It's the box number 7. This little beige-colored box. T prime is your velocity vector times the curvature times the unit normal vector. Okay? Again, that's the first derivative of the unit tangent vector. So this thing right here is the velocity vector, not vector, speed, v of t times the curvature as a function of time times the unit normal vector. Okay. Now you remember that the first derivative, the unit normal vector, which we wrote up here, is the first derivative of this. So your magnitude of that first derivative of the unit, I can't talk, unit tangent vector, that's what this is, the speed times kappa, curvature. Okay, you can go back and review that. All right, well, what does this give you? This is your speed. First derivative of the speed is what we call the linear component of the acceleration. Which another way to refer to that is the tangential component of the acceleration. So this is what we call a sub t. Okay, now that's in the direction of the unit tangent vector. And this is the unit vector. Okay, plus, okay, and this is v squared times kappa, speed squared times kappa. Okay, now that has a meaning. The velocity, and not velocity, speed squared times the curvature. This is what we call the unit, the normal component of the acceleration. Okay? If you remember back with a circle, the curvature is 1 over the radius. This is your v squared over r then. And that would be of any curvature that you had. Not just a unit circle, I mean not just a circle, but the radius of curvature is v squared over r, but 1 over the radius of curvature is your curvature. 1 over the radius is your curvature. Okay? So this would be then a sub n, the component in the normal direction, times your unit normal vector. Because your unit normal and unit tangent vector, unit length, the magnitude of the acceleration in the tangential direction, which is your, think of it as your linear acceleration, and then your normal acceleration, which for a circle would be, if you're traveling uniform circular motion, that would be your centripetal acceleration. Of course, if you're uniform circular motion, your tangential component of your acceleration is 0, because your speed is the derivative of your speed is constant, the derivative of the constant is 0. Okay. And that's where I think this next slide comes from. Yes. Okay. This is basically what we just said. Your acceleration as a function of time, which is the first derivative of your velocity vector, okay, is going to have a tangential component, that's a component tangent to the curve, and that will give you your acceleration tangentially, which is your linear acceleration, tangential acceleration, times the unit tangent vector, plus your normal acceleration, which is accelerating toward the center of curvature of that curve. That's your a sub n. Yes, ma'am. No problem. What you need?
So, Dr. Wilson said that...
Okay, wait, let me pause this. Sorry, I just had someone come in with a message, so I paused you again. All right, so that's your acceleration, which is your derivative of your velocity vector with respect to time. You have a tangential component and a normal component. The tangential component is simply the first derivative of the speed, okay, which is your linear component of your velocity. First derivative of that is your tangential component of your acceleration, okay? The normal, the a sub n, the magnitude of the normal component of your acceleration, well, that's your kappa v speed squared, okay? Curvature times your speed squared, which you can also think of it, in fact, to me this is easier to remember, speed squared over your radius of curvature. Doesn't have to be a circular path, circular motion, but remember we said any curved path has a radius of curvature at that point. and that 1 over that radius is your curvature. So v squared over r, that's easier for me to remember than kappa v squared, though they're both pretty easy. Okay? Here is the figure. Sorry, I went to zoom in and my cursor just happened to land on top of the pause button again, so it paused rather than zoomed. Okay. So here is a curved path. Okay? The green curve is no longer a circle, but a curved path. Okay? Your velocity at any time is tangential to the curve. In fact, in the direction of that unit tangent vector. Okay? And as you could guess here by looking at that, since this has more of a component in the tangential direction than the normal direction, you have acceleration in that direction. In between the two of those, there is a tangential component of that acceleration and a normal component. So I wish they had drawn the same thing here. Here's your tangential component of the acceleration, which is basically the first derivative of the speed. Okay? And your normal component of the acceleration is your kappa times your speed squared. In other words, speed squared divided by the radius of curvature. Right, 1 over radius of curvature is your kappa. Okay? So that's splitting that into its components. Now, if that were circular motion, then the acceleration would just be in the direction of n. You have a tangential, your velocity is tangential, your acceleration would all be normal. But since this isn't a circular path, nor a circular path at changing velocities, then you have a tangential component and a normal component. Okay. There's a conceptual insight coming up. Sorry. Okay. I'll condense what they're saying here. The tangential component of the acceleration. Yes.
You said when do you think you'll be able to have the spring?
Schedule in. I hope by the time I leave on Friday.
Thank you.
Okay, thank you.
I apologize.
I'm sorry? Okay, sorry. She came back with another message. Okay. So let's go back up to can't remember where I left off here. Your tangential component of the acceleration is how the speed is changing. Okay, in this example, your acceleration has a component in the direction of that unit tangent vector, meaning that your speed is increasing in that direction. Okay? It also has a component in the normal direction, means you're following a curve. If there was no component there, all your acceleration would be tangential. Since it has a normal component, that means you're changing direction, indicating you're following a curved path, not a straight line path. Now, if that acceleration had been behind you here, that means your speed was slowing down. In other words, your velocity, your speed would have been in the opposite direction of your tangential, which means, well, the speed is changing in the opposite direction. The velocity would still be going in the direction of the tangent vector, otherwise that wouldn't be its direction. But it's slowing down, meaning that its acceleration, tangential acceleration, would be in the opposite direction. So that would be what it would be if the A were on the other side. That would be slowing down in the tangential direction, still going in the tangential direction, but at a slower rate of speed, and your normal is just related to how much is curving, the speed squared divided by the radius. Okay. Now, Here's I swear, sometimes the cursor disappears on this system. There it goes. The system has gotten awfully slow. Yesterday, it was uploading things fantastic, Monday and yesterday. Sometime yesterday afternoon, it slowed to almost to a crawl. I left my evening class uploading. I came in this morning, it was still less than 17%. Of course, the computer had fallen asleep, so it hadn't progressed much. In fact, I think it was less than 10%. So this morning, while I was teaching my first class, it got up to 17%. So, and whereas yesterday, it was uploading before, one class would be uploaded before I finished the next class. Not so since last night. So everything is moving awfully slow now. So when this will be uploaded, I don't know. So here's the giant Ferris wheel in Vienna, Australia, erected in 1897 to celebrate the 50th anniversary of the coronation of the Holy Roman Emperor Franz Joseph I, who I think was Austrian. I think he may have been I don't know if he was the first and only or whatever, but he was the one they celebrated a lot. Okay? Well, that's circular motion, and as long as the speed is constant, that's uniform circular motion. But when this just begins turning and the speed is increasing, then you have a tangential component of the acceleration, which is you change the speed, and a normal component. You always have the normal component changing your direction, pointing toward the center of the circle. Okay? But once it completes its acceleration, speeding up, then all you have is a normal component, because there's no longer any change of speed. Then when you get near the end of the ride and it starts slowing down, now you have a negative first derivative of the speed. In other words, you're slowing down, so your acceleration, the tangential component of acceleration is in opposite direction of the motion, okay? But still you have your normal component, okay? So this leads to example 6. The giant Ferris wheel at Vienna has a radius of 30 meters. That's pretty good size. So I'm going to have to shrink this to write on it. So this radius here, whoops, I wasn't in the center, was it? This radius is 30 meters, okay? That's your capital R, okay? Assume that at time t equal t0, the wheel rotates counterclockwise, so it's going in that direction, with a speed of 40 meters per minute. Okay? So your V of t at t0, at time t0, is equal to 40 meters per minute, which is not very fast. 2/3 of a meter per hour, okay? Because there's 60 minutes in an hour. Did I say that? No, I said it backwards. That would be 2,400 meters per hour, okay, which would be 2.4 kilometers per hour. Not all that fast, but it's moving, okay. Enough of that. It's slowing at a rate of 15 meters per minute squared, which means your V prime of t at t0 is negative 15 meters per minute. Okay, this is all translating as we read. Find the acceleration vector. This morning, this fly was bugging one of my students, and it just decided to come and start bugging me. So I managed to squash it. Okay. If you were here, you could have witnessed that. Okay. Find the acceleration vector A for a person seated in the car at the lowest point of the wheel. That's somewhere right down here. Now, you can't see that, so let me get a good light color, like yellow. Okay, so the person seated right down here at the lowest. What is the acceleration vector for a person seated there? Okay? This is velocity in this direction. Okay, that's that vector. Okay? Its speed is 40 meters per second, so that's the magnitude of that velocity. But it's slowing down, meaning it has, and I'm just going to make a guess here, something about like this will be the acceleration vector. Because it's slowing down tangentially, but still has a normal component, of course. Okay? So, what does it ask? Find the acceleration vector. So let me go back to black. So the acceleration vector as a function of time, remember, is your v prime of t in the tangential direction plus v squared over r in the unit normal direction. Okay? So this won't be too hard to write. We already know what minus what v prime of t at t0 is. That's minus 15 meters per minute in the unit tangent direction plus v squared would be 1600 divided by r, which is 300 meters. This is meters per minute. Actually, it's meters squared per minute squared divided by 300 meters. The radius is 300 meters. And this will be in the unit normal direction. Okay? Now, that will be minus 15 meters per minute. Oh, wait. Derivatives here. Yeah, I wrote it wrong. Or I wrote it in the black and didn't see it. The first derivative of your speed is in meters per minute squared. Okay, because it's change of speed per unit time, and that would be meters per minute squared. So this is meters per minute squared in the unit tangent direction plus 16/3. Let's just leave it like that, 16/3. And here minutes cancel out, and you have meters per minute squared again in the unit normal direction. Now, I don't know if that's how they want it written, but sure enough, that is what they All right. Oh, I'm sorry. I misread. I had the radius of 300 meters. That was an M there. This is only 30 here. So that would just wipe out 1 0, and it's 160 divided by 3, which would be negative 15 meters per minute squared in the unit tangent direction plus 3 will go into that, 3.3 they say. I don't know if they got that in the unit normal direction. And this will also be meters per minute squared. Okay. In the unit normal direction. And that's exactly what we've got. Okay. So here's theorem 1. No, it isn't. Oh, this is what I was trying to draw on the circle, and my approximation is not far from what they've got here. Okay, unit tangent, the speed in the direction of the unit tangent vector is in that direction. They don't list it here, but that was what they told us was 40 meters per minute, okay, in the direction unit tangent vector. The unit normal vector in that direction, you have 1 over r, which is 1 over 30 times 40 squared, your velocity, linear velocity squared, which is what they gave us also. That'd be 1600 divided by 30. The calculation we just made, that's 53.3 in the unit normal direction. Okay. So that then leads to theorem 1 in this section. Okay. Trying to keep up. Yeah. So here's your theorem 1. Tangential and normal components of acceleration in the decomposition where your acceleration vector is the acceleration in the tangential direction times the unit tangent vector plus the acceleration in the normal direction times the unit normal vector. We have, and here are some other ways to express this. That component in the unit tangent direction is the dot product of the total acceleration vector times the unit tangent vector. Okay? And if you think what that is, that's the component of the acceleration in that direction. Okay? So that makes sense. Well, what is unit tangent vector? It's your velocity vector divided by its magnitude. So you could say that's A dot V divided by the magnitude of V. Okay? Now, that's not a hard thing to calculate. Okay? If you're given a displacement vector, take a derivative, you get the velocity vector. Take another derivative, you get the acceleration vector. Go back to velocity vector, determine its magnitude. Okay? Take the dot product of acceleration times velocity. Remember, it doesn't matter which order you do those in a dot product. Divide by the magnitude of the velocity vector. Okay? That gives you your acceleration, your tangential component of your acceleration vector. Now, how do we do the unit normal, the component of the acceleration unit normal direction? Well, that's A times N, but N is not that particularly easy to calculate. You can do it, but it takes a lot of effort. So rather than A dot N, or doing some other ramification of it, just you've already got the acceleration vector, the total acceleration vector. Take its magnitude, square it, subtract from that the unit tangent vector acceleration you just calculated, and take the square root of the difference. Because you know that the tangential component plus the normal component of the acceleration vector is going to be the acceleration vector, so it's far easier to do it with the square root form. Okay? Now, if you were to do the entire vector, not just a component of the vector, a sub t times unit tangent vector, what you're multiplying then by is The unit tangent vector is the velocity vector divided by its magnitude. Well, we already divided by the magnitude once. If you recall, v dot v is the magnitude squared. So you have exactly what you have here, a dot v, okay, over this was square root of v dot v. This was v over v dot v, so you just have v over the square root of v dot v, and product of those is v dot v. So again, this is a very hard thing to do. If you know r, you know you take a derivative, you get v, take the derivative, you get a, dot product of a with v, dot product v with v. That gives you a scalar number, rational expression, and then multiply that by your velocity vector, which you just calculated. And again, the easiest way to do the difference of that, to find the unit normal component, is just take your original total acceleration and subtract from that your tangential component, vector subtraction, and you have your tangent, you have your normal part of that vector. Okay. Let's move on to example 7, which I think is right here. Okay. All right. Let's see, what is it? 125. We go until 155. So I got 30 minutes. I'm going to have to stop for something else to drink. My throat is getting raw again, so let me pause. All right, sorry about that. I still can't seem to clear anything. So I hope I can just keep going for the rest of the class. Okay. I think we're ready for example 7. I believe this is the figure for it. It says decompose the acceleration vector A of r of t, here it is equal to t squared 2t log t. Yeah, natural log t. Into tangential and normal components at t equal 1/2. Okay? And this is the figure here. Now, I can't remember, one of the figures like this is off. Okay, I don't remember if it's this one or not. This is a new edition of the book. They may have gotten it corrected. It seems like in the old edition it was way off. But let's see what we got. There's your r of t. Okay? And it says decompose the acceleration vector into tangential and normal components. Well, what we've got to do first, I hope you realize, is take a derivative. All right? I can't see my pen here. Okay? I'll just call it r prime of t, which, by the way, is v of t, and that's equal to, this is so small on my screen, this is a loaner computer, and the screen is small itself, and then the window that it puts it in is even smaller, and it's almost impossible to see, so I'm going to have to look at the book. Yeah, that's 2t, comma, 2, yeah, comma, 1 over t. Okay, that's the velocity vector at any time t. Okay? Now, the acceleration vector, which is the first derivative of the velocity vector, which is the second derivative of the displacement vector, is 2, 0, minus uh, 1 over t squared, I think. Let me think. Let's rewrite this as t to the minus 1. Yeah, minus 1 over t squared. Yeah. Now, they wrote it this way. Minus t to the minus 2. Okay. Either way is fine. Okay. They probably wrote this one like that. Okay. So, there's your acceleration vector. Now, what did they say do? They said decompose that acceleration vector that we just calculated, a of t, into the tangential and normal components at t equal 1/2. Okay? So I think it's safe now to plug in the t equal 1/2. So I don't think we need the r vector anymore, but we do need the v vector. So v at 1/2 is going to be 1, 2, 2. Because if t is 1/2, 1 over t is 1 over 1 over 2, which is 2. The acceleration vector at t equal 1/2, okay, is then 2, 0, minus 4. Okay? Now, oh my goodness gracious. My back is so stiff. Painful. Okay. Let's go back to Theorem 1, and let's write this in the simplest form. Okay? Your a sub t is a dot v, doesn't matter which order, divided by magnitude of v. Okay? Well, I think we can do a dot v pretty easily. It's 2 plus 0 minus 8. So that's negative 6. Okay? Over magnitude of v squared, the square root of 1 plus 4 plus 4, that's going to be 3. Yes. 1 plus 4 plus 4, that would be 9. Square root of 9 is 3. So this is negative 2. So there's your component of your acceleration vector in the tangential direction. Okay? Now, let's do the magnitude of A. That is the easy way to do your normal component. Okay? Magnitude of A is equal to the square root of 4 plus 16 is the square root of 20. Right? Okay? Now, that squared, the square root of A squared, is obviously 20. Minus the tangential component squared, okay? Well, the tangential component squared is, tangential component is minus 2, squared is 4, so this is equal to 16. Okay? Now, I'm not writing everything correctly. Take the square root of 16 and you got 4. Okay? And it's principal square root, so we leave it like that. So the normal component of that acceleration vector is 4. Tangential component is -2. And I was just checking to see if everything added up, and sure enough, -2 squared, 4 plus 4 squared, 16, is 20 squared or 16, that's, Okay, so here we have it. Your acceleration vector at 1/2 is equal to, there it is, -2 times the unit tangent vector plus 4 times the unit normal vector. Okay, I think that's all it's asking for. -2t plus 4n. Now they did a whole lot more work to get there. I don't know why they strung it around. They did the unit tangent vector. They did a sub n in. They did just a lot of stuff that seems totally unnecessary. Okay, but they did it. Okay, that was the answer they're looking for. Now, let's take a look at this, and let's see if they got this right. If this is your, goodness gracious, it's hard to read. Yeah, this is your positive x, there's your positive y, and there's your positive z, right-hand system. Okay? Your displacement vector, we didn't actually calculate t equal 2, but that would, t equal 1/2, that would have been 1/4, 1, log of 1/2, which is going to be a negative number. Okay, so let's see if they have that. And again, it's hard to represent it in thing, but you had, what did we say the first was? 1/4. So you haven't gone far on the x direction. It looks like you're going a lot further than they indicate here. And then your y direction is going to be, where was it? 1. So in the y direction, it's a +1. Kind of looks like they got those two components backwards, but let's see. And then the z component is going to be negative. All right. Some sort of negative number. The z looks okay. So with the unit tangent vector moving in that direction, meaning the velocity is in that direction, the curvature is in toward the center of curvature, so it's in that direction. Those are unit vectors. Just represent them as a unit quantity. Now, the acceleration vector has a negative component along t and a very positive component along n. Yeah, looks like they got that one as well as could be expected. We don't have really a scale to go on, so it looks like that's probably true. All right, so there was example 7. Let's move on to example 8 if we can. Okay, let's see if we can set this up for now. Okay. This is non-uniform circular motion. Figure 9 here shows the acceleration vectors of 3 particles moving counterclockwise around the circle. In each case, state whether the particle's speed is increasing, that speed v is increasing, decreasing, or momentarily constant. Okay? Now, it's moving this way, not necessarily at a constant speed. In fact, if they show this and you see the acceleration has its tangential component is negative to the motion, that means it's slowing down. So this will be a slowdown. I'm going to write it. So this will be slowing. Okay. The second one, what it's indicating to you is that the acceleration vector is in the same direction as the normal vector, toward the center of the circle. So just at that moment, it must be at a constant velocity, because it acts just like uniform circular motion. So that would be momentarily constant. Okay, and the third one there, the acceleration vector is in the same, or has a component in the same direction of the unit tangent vector. That means its tangential component must be positive. The normal component just keeps it turning, okay? May affect curvature or whatever. So this would be speeding up. What's the way they phrase it here? The speed is increasing. Okay, I can't write. Got it. Speed increasing. Okay, speed decreasing, momentarily constant, speed increasing. All right, example 9. I don't think they have a figure for it, so let's use the same figure, just erase what we've got here. Man, thought it was going to be easy to finish, but goodness gracious. I've had a dull headache since Monday, not constant, but just off and on. And I hardly ever have headaches. This has to be one of the longest lasting one I can remember. It's not pleasant. So let's do example 9. Find the curvature, same figure here, find the curvature at 1/2 for that path that we just had. Okay? Now, wish I hadn't have erased it now. Trying to, I'll just look up above. I mean, this figure here, I'm sorry, it's not erased, it's here, okay. Figures, example 7, okay. Find the curvature kappa at 1/2 for this figure, okay. What you might recall, hopefully you do, let's flip back another slide. Another one. Here we go. Is this it? No. I guess. Here we go. This is the one. All right. Your A sub n that we calculated is equal to v squared times kappa. Okay? So here we have A sub n, here it is right here. A sub n is equal to v squared times kappa. Okay? Let's go back to the one we were working on. Well, that one. Okay? Well, your A sub n here was 4. This is equal to v squared times kappa. Well, we knew what V was. It was 3. That was your V. The magnitude of that was 3. So this is 4 is equal to 9 times kappa. So your kappa here is equal to 4/9. Okay. I haven't been keeping up with units very well. Goodness, my head hurts. But we see that 4 is equal to 9 kappa. Kappa must be 9 at that point, okay? Which means your radius of curvature at that point would be 9/4. And that's exactly what they got here. So that was a fairly simple, straightforward problem using what we did before. All right. The summary here, and these are some of the items in the summary. Okay. The unit tangent vector, the practical way of doing it, it's usually pretty easy to calculate the velocity vector. If it wasn't given, they're given the radius vector, displacement vector, the first derivative of that is velocity. Take that velocity, divide it by the magnitude of the velocity. You can leave it in terms of time, or if they give you a time, calculate it. The unit normal vector. Once you have that unit tangent vector from step 1, take a derivative of it. It's no longer a unit vector, so take the magnitude of that derivative, divide the derivative by its magnitude, you've got the unit normal vector. Okay? Now, for any curved path that an object is taking, the unit tangent vector is tangential to that curve, and the unit normal vector is on the inside part of that curve. However that curve is curving inward, the unit normal vector is in that. They're always perpendicular to each other. I want to say always. I think they're always, because your radius of curvature is perpendicular to the unit tangent vector there. So I think it's got to be. So that's the unit normal vector. The tangential component of your acceleration vector is the first derivative of your speed, okay? That's your tangential speed, which is a dot t, but that's sort of hard to do. Much easier to do a dot v divided by v. Your unit normal vector, okay, if you have enough information to tell it, you can use the formula kappa times speed squared. I found it easier to remember because of its centrifugal acceleration, v squared over r, okay, where r is the radius of curvature at that point, okay. If, however, you don't have, you usually have the speed, because you've already calculated the magnitude of velocity, so you already have that speed, and just square that. But the kappa, usually you don't have kappa, or you don't have the radius of curvature of the osculating circle there, so that sometimes is not an easy thing to have. Far easier, you already calculated the acceleration from up here and here, okay? Just take the magnitude of that, square it, subtract from that the absolute value, you might say, of that tangential component. I have some issues of how they represent things. This should not be bolded. That should be this expression here. A sub t. It's a scalar quantity, not a vector's quantity. So that A should be this little a there. That makes it look like it's a vector. It's not a vector because you don't take the absolute value of a vector. You take the magnitude of a vector, and that's not what this is called for. Now, the other way you can do that is expanding your tangential component, and there's this expression, and A minus that is going to be your normal term. Okay? But that's a little awkward. All right. So that finishes section 13.5. Okay? If you were here, we do preliminary questions. Since you aren't, I don't know if you want to do them or not. Let's just read through them quickly and see if there's anything magical here. If a particle travels with constant speed, must its acceleration vector be 0? If it was in a straight line motion, yes. Curving motion, definitely not, because there is a change of velocity with a change of direction. So this 3.5 preliminary question, no, since a particle may change its direction even though its speed is constant. Number 2, for a particle in uniform circular motion around the circle, which of the vectors v of t or a of t always points toward the center of the circle? Well, definitely not v of t. That is moving along the circle, so that's going to be tangential to the circle. The a of t points toward the center. Okay? 2 is a of t. Number 3, 2 objects travel to the right along a parabola y is equal to x squared. Here goes my voice again. Sorry. With non-zero speed. Okay, so they are moving. Which of the following statements must be true? 2 objects travel to the right along the parabola y is equal to x squared with a non-zero speed. Which of the following statements must be true? The velocity vectors point in the same direction. Now, if I'm reading this right, 2 objects travel to the right along the parabola, y is equal to x squared, with a non-zero speed. Which of the following statements is true? The velocity vectors point in the same direction. Well, if they're at the same position on the parabola, okay, then the velocity vectors would point in the same direction because they may have different magnitudes, but they would point in the same direction. If they're at the same point. Now, if they're separated, just moving to the right, no, the velocities wouldn't be. So all right. Let's see if B lends any light to it. The velocity vectors have the same length. Not unless they're going at the same speed. So that wouldn't necessarily be true. C, the acceleration vectors point in the same direction. Okay. Now, 2 of those questions sound like they're at the same point. Okay? And if they're at the same point, velocity vectors must point in the same direction, but they may not have the same length. So that would be A, yes, B, no. The acceleration vectors point in the same direction. Not necessarily true. Okay? The normal component would, but not the total. So I think A, if they're at the same point, A must be true. B and C would not necessarily be true. Let's see what they say. The velocity vector always points in the direction of motion since the vector. Oh, wait, no. Statement A, the velocity vector points. Yeah, they were at the same point. So, yeah, it is A. The other two not. Number 4, use the decomposition of acceleration. We're out of time. I'll let you work on the rest of those if you want to. Let me just give you your homework exercises. Do number 1. Do either 3 or 5 or both. Do either 7 or 9 or both. Do either 11 or 13 or both. 15 or 17 or both. Do any of the odds 19 to 25. Do any of the odds 27 to 31. Do either 33 or 35 or both. Any of the odds 37 to 43. Any of the odds 45 through 55. Okay? Some of those may be a little esoteric, but do what you can on them. If you can't do much, don't sweat it. Further insights and challenges you don't have to do. I just always look to see if there might be a potential paper topic. I don't see it. All right, next time we'll sort of do a real hand wave toward 13.6, planetary motion according to Kepler and Newton, mostly because you can get some good paper topics out of this, and also to expose you to it, but we won't do it in gory detail. I doubt if you'll ever need to do it, but it's a good thing to be exposed to. It was a lot of physics, calculus, other things came out of this problem. So that won't take us long to do the slideshow. That's it for the chapter. I've already given you chapter test, and we'll get started at chapter 14 next time. So we'll just do a very quick PowerPoint show on 13.6 and then move on to chapter 14. Good deal. Hope someone shows up. Have a good weekend.